So we'll talk about a field campaign that we are actually start to plan. We don't have any funds yet for none of this, but it's a project that has been on the mind of several people from US, Brazil, and also Argentina. And the name so far is Relâmpago. Relâmpago, the acronym for this is Remote Sensing of Electrification, Lightning, and Mesoscale, Macroscale Processes with Adaptive Ground Observation. Why Relâmpago? Because it translates like Portuguese and Spanish, both is lightning. So we so far chose this acronym, but it can change. So the objective is to study the mesoscale convective systems in the South America. So it's international multi-industry field program that we are trying to invite, and we will study the multi-scale aspects of intense. I will read from intense organized convective systems that produce severe weather in subtropical South America. So the idea for this campaign comes from TRIM, actually. There is an article from Ed Zipter and co-authors in 2006 that studies where are the most intense thunderstorms on Earth, seen from TRIM. And the thunderstorms that gets the outstanding for almost everything, for lightning, for microwave, like the lowest microwave temperature, and everything, like the tallest ones, they are in Argentina, in North Argentina. So we have like a region with very active convection, like unique intense vertical structure, a broad horizontal organization, and lightning production. This data this data do not, we want to see, let's go to the other one. So we have several prior works where we can see some studies about the influence of South Atlantic convergence zones and also the role of subjects in the production of these storms. And now CHUVA, we had studied like the mature to the dying phase of the mesoscale convective systems. And we know now that they do start of Argentina and go through Brazil, but we have never characterized these systems from the ground base. We only know from satellite. So what we have learned from the previous campaigns, like SALJAX in 2003, is that the position and intensity and internal structure of the SALJAX can get the interannual and diurnal time scales and global synoptic scales. And also the network deployed during SALJAX, it was not enough to describe the mesoscale environment and the convective initiation. We did find a relationship between SALJAX, the South Atlantic Convergence Zone, the Chacolo, and the low-level jet on the synoptic scale. And it was possible to assure the relationship between the mesoscale convective systems and the low-level jet, but they only had one flight that actually did that, and the radar was on the flight too. So, and also sounding network that was deployed during that campaign, it was not possible to clearly understand the mesoscale environment because it was launched, the soundings were launched only at 6 UTC during overnight. During CHUVA we had some radar network, like as you know, not the X-band, but the regional one. We could study the large-scale processes and also we could see that in southern Brazil is characterized typically by the organized deep convection associated with the large amount and strong winds, and the severe weather that is related to hail is located over central Argentina and not most in Brazil. And one thing that really got our attention is that the numerical weather prediction models, they varied a lot in the success of predicting this, the initiation, propagation, speed, intensity, and organization of the convective system. And we were like every day trying to guess what would happen. The numerical models wouldn't tell us. So the main questions we are trying to answer is like severe weather. From the Cecil and Blankenship article that was recently published, we can see that the hail index from M E is over this region here. These are the dark spots are around here. It's like a pre-index for hail and several, that would be that. And so, but there is another study from Matsuda and Salio that from the observation point where we have more hail and dust and heavy rain is actually on the border of Brazil, like surrounding this area, not inside this area. So we don't know if it's like not, as it's not so populated, so we don't have much reports, or if there's something on the satellite retrieval that we are missing. So the question is like, why do many storms in northern Argentina stand out among the strongest on Earth in satellites observation without ground-based verification or strong reputation about the violence of these storms? And does the pre-convective environment and ground truths confirmed severe thunderstorm in South America display like a loaded gun profile, but it's not actually being triggered? Is an elevated mixed layer leading to early convective initiation also observed over Argentina in days of severe thunderstorm? If so, there is an observed South American dry line triggering such storms. Can we improve microphysical models and forecasts with new information that might be applicable within and beyond this region? And on the cloud microphysics and electrification, we know from TRIN, like this is a plot for the extreme 1% of events observed from TRIN, where is the maximum height for the 40 dBz, and also the flash rate. It's over Argentina, but combined flash rate and 40 dBz. So we want to know what leads to the extreme tall radar reflectivity structure of storms in this region, like going with 40 dBz up to sometimes height of homogeneous freezing temperature. Like here we have maximum heights of 15, like very, very high for 40 dBz. And does the extreme vertical structure and dense ice production in these storms lead to unique drop size distributions in these storms? We don't know yet. Like we have very large drop size distributions on the ice cores on the ground. Does the broad structure of the systems lead to enhanced charging and lightning in the anvil and the stretch forms region? And does the extreme structure of these storms can lead to sprites and the transient luminous events production compared to U.S. Central Plain? That's like this is a picture of one of the sprites. So on the life cycle of this mesoscale, we want to know what controls the diurnal cycle of convective system intensity and the vertical structure and mesoscale organization in the Lee Andes. What is the role of microphysics and kinematics processes in leading the upscale growth of convective clouds into MCSs and then in the end into mesoscale convective complexes? Does the extreme intensity of the convection in the region impact the morphology of the convective storms and vice versa, and how? And are these inferences of predictability of these processes from observation? Like how well do cloud resolving modelings and the numerical weather prediction models can resolve this morphology in a study like in a seasonal time scale? We don't know yet. Like on the pre-environment for that, what are the synoptical and mesoscale flow features in this region that and how do they dictate the triggering the convective systems and the environment for storms to grow upscale into mesoscale convective systems? How the boundary layer control the evolution of the low-level jet and the evolution of the mesoscale and complexes, and how do the katabatic flow near ends evolve and generate and initiate the large convective systems? This is something that we have noticed in CHUVA, that they are initiated from the katabatic flows from ends. And the low-level jet produce like a very strong transport between the Amazonia, Paraguay, and North Argentina biomass, and as well as dust outbreaks from the south, where you have the deserts down here. So how do they influence aerosol? How does this aerosol can influence the development of a large convective system? And on the prediction standpoint, as I already showed, the numerical weather prediction, they don't do very well. And like, are they missing some important data for a simulation? Or are they missing actually physical processes inside? Does the large zonal soil moisture gradient in Argentina control the intensity and the structure? How data sets are missing in the order for a more accurate nowcasting and short-term prediction? What are possible inferences and limits of predictability on synoptical to intraseasonal timescales for this type of convection? So the strategy is to use the ground-based radar network. This is some outlook for 2014. Actually, there's a radar missing here in Cascavel. There will be another one here, getting this gap from Singapore. And in the end of 2013, we might have Argentina, most of northern Argentina part covered by radars. So they will be C-band, Doppler, and some dual pole. So going to that region again where we have that index for severe weather, that is here, this 2 points. We are targeting this lower part here due to logistics, that there's more people living there, but we are going a little bit up north too. So this is only like what we have in terms of soundings, and we have like most of Brazil covered, but not Argentina. So we'll be covering that region too, like here. This is just for you to get where you are. Here's Buenos Aires. Here is South Brazil, like Rio Grande do Sul. Foz do Iguaçu is up here. So we are targeting this area here, where we will install 5 sites, sounding sites. We are planning to ask NSF for ESPO. So ESPO would be placed near one of these radars, like covering the other part. And we are also asking for the DAO radars, the Doppler on wheel ones. So they will not actually chase the storms, but they will be moved as the prediction of the storms. So that we can have a dual pole or extend the network furthermore. And we're also planning a lightning mapping array that would be under ESPO, and a mobile sticknet, and a supersite, precipitation supersite from NASA under also the radar coverage. We are also reaching NASA and NOAA to get more instrumentations like a line of disdrometers and rain gauges for QP, and also NPO radar, so we would have another one up here, and NASA Year 2 aircraft, where we want to put downward looking radar, passive microwave radiometers, the GLM airborne simulator, that's the Lightning simulator, and also the Lightning package, and drop sound. So the aircraft would stay in Buenos Aires and then fly through where the thunderstorms are. Like, it's more like this. This is one of the cases during Chuva Sul. So usually it's to collect these several convective cells that initiated in a point and travels through South Brazil. So the aircraft would go into this line of storms and do the measurements. So the assets that we are envisioning is like 6 or 8 weeks of the whole operation with intensive operations campaigns inside this 8 weeks. So as I told you, NSF would bring ESPO and also the ISS, the Dow radar, and the Texas Tech University StickNet. And we are also trying to get GPM and GOZAR on board. From Brazil, we will have sounding launch facilities, the StickNet from Federal University of Santa Maria, light mapping array from INPE, ground-based electric field mills, and also balloons. There's actually from Japan that we will try to see if they want to participate, getting profiles of the vertical field and video charge particles measurements, and also high-speed cameras. From Argentina, they have the 2 operational C-band dual pole radars that they will be installed by 2014, and the existing dual pole at Paraná. And they will also have a mobile sounding facility and aerosol and thermodynamics. And we want also to get Chile and Paraguay, maybe Bolivia, just like to cooperate and host some of the instrumentation. So far, the science group, starting one, it's led by Steve Nesbitt from University of Illinois. Then we have Dan Cecil and Tim Lang from Marshall Space Flight Center. We have Karen Haslund and Bob House from University of Washington. And I don't remember the D name. Do you know? I don't remember the name. Then from Brazil, we have Luis and myself and Hernani from the Federal University of Santa Maria. And in Argentina, we have Paolo Salio and Celeste Saulo. And this, that I don't know the first name, please. Gracias. And the D. Brandon. Then. So the near term plans that will be reaching out other sciences like here and modeling like the interests of each one and craft a white paper by this year. And we are also seeking WMO World Weather Research Program and World Climate Research Program to endorse this field campaign. And that's it. Yeah, it's only 2016.
The proposal, and we hope that the team group will improve and increase the value
Do you know where?
after the volcano, there's a funding for building a rider on every airport. So
It's
the
not.
main thing is not around the area, but
Yeah, actually, there are also parts something that it's not supposed to be.
Okay, so we are going to close the session today. So great to meet some today.
We are going to the pizzeria that is nearby here. 10 minutes, I guess, by car. And we have Inky's van. Is that full or not? You know the van? We have my car, Carlos' car, Thiago's car.
My car, there's enough car for it.
Yeah, I think there's enough car for everyone. So, okay, one car.
Good. So what time?
We can leave now if you want. É Canto da Mata.
Canto da Mata.
Canto da Mata. Você mora do lado mesmo.
Okay, thank you.